Quantum-safe networks are no longer a distant vision. They are becoming a deployment reality. Current optical infrastructure is the foundation of those networks, and layer 1 encryption is where quantum resilience begins. My name is Paola Osorio, and I'm a product line manager for optical systems here at Ciena. Today, we're going to talk about quantum-safe networks. At Ciena, we offer high-capacity, high-speed connectivity with our optical transport solutions, and when we combine that with AS256 GCM encryption, we're able to offer a very powerful layer 1 encryption solution using our Wave server family of products. Our solutions are FEP certified 140-3 level 2 as well as common criteria certified, which has opened the door for us to implement and deploy our solution across different industries and different network applications all over the world. On top of that, we have implemented quantum-safe technologies like QKD and PQC to help our customers transform the current classical networks into quantum-safe networks. Our encryption solution is designed to implement NIST-certified PQC algorithms. When customers deploy our encryption solution with PQC, they get quantum-safe encryption right out of the box, meaning they don't have to go through an extra step or procedure to enable PQC. It's going to be there by default. One key requirement that we vendors need to be aware of when implementing PQC algorithms is that we need to become crypto-agile. That means that we need to adapt quickly to new encryption protocols or algorithms without disrupting major current operations or underlying infrastructure. So we have added that flexibility into our design so we can adapt quickly as more PQC algorithms will be standardized. On the right-hand side, you can see our Wave server platform, where we're showcasing our next-generation WaveLogic encryption using WaveLogic 6E. This technology can do up to 1.6 terabits of encrypted capacity per wavelength. As you can see, this LED has 2 line ports based on WaveLogic 6E, meaning that this LED can do up to 3.2 terabits of encrypted capacity. When we fulfill the Wave server platform with up to 4 of those LEDs, we can do up to 12.8 terabits of encrypted capacity in a 2RU platform. With QKD, we have implemented an external key mode of operation based on the ETSI 014 QKD REST API. This has allowed us to interop with other QKD vendors that have also implemented the same API. We have been able to successfully validate our solution with multiple QKD vendors and participated in multiple variety of projects, including commercial deployments, research and education test beds, as well as different POCs with different customers. As QKD technology evolves, the acceleration of its adoption will depend on how seamlessly it will integrate with existing optical infrastructure as well as with existing systems that serve these networks today. When we talk to different customers, their key requirements become for the quantum channel to have a stable co-propagation with C-band traffic as well as L-band traffic. The quantum channel should have a high tolerance to network impairments. The system as a whole should have a proper failover mechanism in the case of a fiber cut or a system failure, and of course be low cost and scalable. We continue to work with different QKD vendors that are advancing the technologies to meet these requirements and are open to continue to working with other vendors that share the same goals. Fiber-based QKD has a distance limitation due to the properties of quantum mechanics. This makes it suitable mostly for single-span metro applications, but that's just a small piece of the global connectivity infrastructure. Most data travels across cities, regions, countries. Most of the internet traffic travels across submarine cables. Hyperscalers link their data centers between different countries and continents to distribute the AI workload. So it is essential for us to bring QKD technology to these type of networks. Although there is research ongoing about quantum repeaters, which is a technology that is looking at extending that distance limitation from a terrestrial perspective, the practical deployment of these technologies is still a few years away. Satellite-based QKD uses free space optical links between the ground stations and orbiting satellites to securely create and distribute quantum secure keys. These ground stations can be separated by thousands of kilometers, but once they share a secret key, we can use that key to encrypt the data that is going to travel across the terrestrial optical infrastructure. By bridging space QKD with the terrestrial optical infrastructure, we're getting a step closer into our end goal of having end-to-end quantum secure data transport. This is why we have been part of the Quantum Encryption Science and Satellite Project since 2023. This is a Canadian Space Agency project that is run by the Institute for Quantum Computing in the University of Waterloo, which mission is to help Canada to build a quantum secure communication infrastructure. We're very proud to be part of this project, which goal is to demonstrate QKD from space. It will aim to establish an optical free link between the ground stations and the orbiting satellites, where the satellite will act as a secure relay node. It will act as an intermediary between the ground stations to allow them to exchange the keys. Our role as being part of this project is to take those keys and use them to encrypt the data that is going to traverse the optical fiber infrastructure already in place between the ground stations. There are valuable insights from this project. From Ciena, we want to understand the commercial viability and technical feasibility of this type of projects in real use case scenarios. Our first priority, of course, is multi-span network applications or long-haul networks that form the backbone connectivity of all traffic. And if we can get one step ahead, can we look into data that travels through transoceanic submarine cables? And the reason for that is even if quantum repeaters were to be deployable in the future, the current infrastructure of these submarine cables does not allow for a quantum repeater to be put in there. And so satellite-based QKD could be a solution in this case. And finally, we can look at a constellation of satellite-based QKDs that can provide continuous global quantum secure coverage. It's very exciting to see how the industry has come together to provide quantum-safe solutions to the current networks that we have today. At Ciena, we're very excited about being at the forefront of this innovation by bringing the industry-first 1.6 terabit quantum-safe encryption solution to the market. Thank you.